Okay, so last time we discussed the orthonormal vectors, and so if you have orthogonal vectors, then they are automatically going to be linearly independent, and also we talked about a matrix whose columns are mutually orthogonal vectors, so mutually orthonormal vectors. Then and on top of that, if that matrix is a square matrix, then we say that matrix is an orthogonal matrix. And in case of the orthogonal matrix, the inverse of the orthogonal matrix is very easy to obtain. Just take a transpose. That's it. Today, we still want to talk about. I will still want to talk about the why the orthonormal bases are important, and how they are, why they are advantageous in computation. So the projection onto a subspace spanned by all right. So first, let me compare for any given subspace V. So let me compare just random basis vectors and orthonormal basis vectors. Suppose I have a random basis vectors from V1 to Vn in Rn. Now choose any vector V, and well, because of our theorem, so I must be able to write down my vector V as a linear combinations of them from V1 to Vn. Writing V as a linear combination of vectors from V1 to Vn. So this is simply finding these coefficients from C1 to Cn. Hold on. So okay. Sorry. So let me just think a moment. Okay. Good. Sorry. All right. So now, how do we find such coefficient from C1 to Cn? Using matrix, this equation can be rephrased as V is V1 Vn everything times C1 Cn. So to find each of these coefficients, then you will need to solve this system of equations. So this is a system of n equations and n unknowns. And because we are assuming that these guys are linearly independent, so therefore this is a full rank matrix, so must be invertible. So you can find exactly one unique solution for this. And solution is these numbers. So basically, finding such a coefficient requires at least n square many multiplications. Well, in terms of the time complexity, so complexity of this algorithm is a square function. Square is not that large, but at the same time, which is not so small. So it takes a significant amount of time and effort to find these coefficients from C1 to Cn. But on the other hand, what if we have the orthonormal basis for the same space? If so, Q1 to Qn is an orthonormal basis, then by same logic, so being orthonormal implies that these guys are linearly independent, and I have n linearly independent vectors in n-dimensional vector space. So these are bases. So vector V can be written as a linear combinations of these orthonormal basis vectors from Q1 to Qn. And in this case, finding these coefficients requires less effort than before, because you take an inner product with the vector V with the ith vector orthonormal basis vector Qi, then this is Qit inner product with this, then this is, and because of the linearity, so this guy times this guy times that, this guy times this, but everything goes to 0, but the ith one, Qit Qi, and the length of each of these basis vectors is 1, so this is Ci. So Ci is Qit V, which is on the other hand, so at the same time, this is Qit times Qi. I think I have seen this before. This is a Qi component of the vector V. So if you project the vector V onto the one-dimensional subspace spanned by Qi, then this number appears, right? Okay. So my vector V, using the sigma notation, I would like to say V is a sum of these vectors, Qit Qi, everything times Qi. Now I think I have seen this before. So this is precisely Qi's component of the vector V. And so projection of onto the one-dimensional space spanned by Qi and V. Okay. So what is the point of this computation? So now if you have suppose that for the same vector space, but if you have the also normal basis, not just a random basis vectors, then computation of this coefficient is way easier than before. And plus, these vectors, so this vector V can be written as a sum of this bunch of projections. In general, this is not true. So suppose that you have a random vector V, and you have some other basis vectors. And what if you project your vector V onto each of these basis vectors? Then once you project your vector V onto each of the basis vectors, and if you take the summation again, then usually that summation is maybe different from your original vector V. But if your basis vectors are also going to basis vectors. Then you take projections of each of these basis vectors and you take a summation. Then it is guaranteed to be the same as the original vector. All right. So now now all we understood the why having also normal basis vectors are so important, because that gives us many computational advantages. But the question is, can I always find also normal basis for any vector space? The answer is yes. Because the algorithm given by Graham and Schmidt. So what is a Graham-Schmidt process or the Graham-Schmidt algorithm? So it goes like this. Suppose that you have some vector space. So any vector space you have. And if you have vector space, then you can find, and you can always find some random basis vectors for that vector space. And given that random basis vectors for that vector space, and if you apply the Graham-Schmidt algorithm to that random basis vectors, then that algorithm will give you back the also normal basis for the same vector space. So this is the Graham-Schmidt algorithm. So because of this Graham-Schmidt process, you're always 100% sure that for any given vector space, you are always guaranteed to find also normal basis for that vector space. Isn't that great? All right. So now I am ready to introduce the Graham-Schmidt process. We consider a subspace V of Rn. And let me say the vector space V is k-dimensional vector space. And suppose that I have chosen a basis, some random basis vector for the vector space B. Set of basis vectors. Okay. What is the objective of the Graham-Schmidt process? That is, we find and also we want to find an also normal basis Q12, QK. Yeah, I should have K basis vectors. That spans the original vector space B. Okay. Yeah, I am running out of space. Okay, and I feel like I can introduce the Graham-Schmidt algorithm by breaking down step by step. Step number one is I want to define my first also normal basis vector Q1, and Q1 is defined by normalizing the first basis vector. So hold on. So what do I mean by normal? What is the normalization? Normalization means for any given vector, you make the length of that vector equals to 1. So how do you make any vector into the length of vector? By dividing everything by its own length. Then you get the parallel vector, but whose length is 1. So Q1 is just a normalization of V1. So this is just simply 1 over V1, length of V1 times V1. Okay. Then this is my Q1. Now step 2. Now I want to have Q2. Q2 is given like this. V2 minus Q1, inner product of Q1 and V2, and multiply by Q1. First, I want to consider this vector. So what is this basis? What is this vector? Suppose that this is my Q1. So I already have Q1 from step number 1. And another vector. So this is my another vector, V2. And so here what I did was very simple. So can you recognize this vector? This vector is simply a Q1 component of the vector V2. So in other words, this is actually nothing but this vector can be obtained by just by projection of this vector onto the one-dimensional subspace spanned by Q1. This is exactly that component, right? So this is Q1 transpose V2 times Q1. Okay, this is a projection. This is simply just a projection. Now, I am subtracting from V2 that projection. Then in that case, the projection of V2, so V2 minus this projection means this vector must be the parallel to this guy, starting from this point and ending at this point. So, so this is V2 minus Q1 transpose V2 Q1. Now I am pretty sure that this vector and the previous vector Q1, they are orthogonal to each other. Why is that? Because, well, this is V2 and I just got rid of every possible Q1 component from V2. I just got removed every Q1 component from V2. Therefore, what remains here is just everything else which is orthogonal to Q1. So therefore, because of the reason, those two vectors must be orthogonal to each other. Okay, just one more thing left. Because, well, now these two guys are orthogonal, but we require the length of this guy to be 1. So again, I have to normalize this. How? Just by dividing this vector by its own length. Then, so you normalize this. Then that is going to be your second orthonormal vector Q2. For simplicity, I will write this is C1 times V1. And I will say this is C2 times this. Okay. All right. The next step number 3. Now I want to have Q3. Q3 is what? Starting from Q3, now I remove every single Q1 component of V3 from V3, and also every single Q2 component of V3 from V3. So given V3, I got rid of Q1 component of V3 and Q2 component of V3. So what remains here is going to be all the remaining component, which is orthogonal to vector q1 and q2 at the same time, right? So because of the reason, this guy must be orthogonal to q1, and at the same time, this guy is orthogonal to q2, right? So and if you normalize this, which I will denote C3 times this, then that is your third orthonormal basis vector Q3. Okay. All right. And this step goes on all the way to step number K. So what is step number K? So we obtained from, at this point, we now have from orthonormal basis vector from Q1 to Qk minus 1. Now, finally, Qk is normalization of Vk minus Vk Q1 minus Q2 Vk Q2 minus minus Qk minus 1 T. I should be extra careful not to mess up my computation. Qk minus 1. Okay. Then this last vector Qk, well, because we normalize this, so this one has to be length 1, and this vector is orthogonal to from Q1, Q2, all the way to the Qk minus 1. All right. So these vectors, because of the construction, I was able to get the K orthonormal basis, orthonormal vectors. And again, I want to call it CK times everything. Okay. Right. I have K relations relating from Q1 to Qk and V1 to Vk. So let me rephrase all of these relations like this. V1 is, so let me go back to the first relation. V1, Q1 is C1 times V1. So I should say V1 is 1 over C1 Q1. And V2 is, where is my V2? Yeah. From the second equation, if I divide both sides by C2 and solving it for V2, then yeah, this component should go here. So like 1 over C2 Q2 plus Q1 transpose V2 times Q1. Oh, right, good. Okay. Yeah, I know this is getting a little bit tedious, but just let me try just one more step. And solving this equation for V3, I have 1 over C3 times Q3 plus Q1T V3 plus Q2T V3 Q2. Okay. Okay, great. And so Vk is 1 over ck qk plus q1t vk q1 qk minus 1t vk qk minus 1, right? Yeah, great. Okay. Oh, just one more thing. Sorry. Just one more thing. So I want to focus on these numbers. Ci, 1 over Ci. All these numbers turns out to be 1 over Ci turns out to be actually Qit, the inner product of Qi and Vi, right? Why? Because we know Q1 to Qk, they are all mutually orthonormal basis vectors. They're orthonormal vectors. So, well, for instance, if just suppose that you have taken inner product of Q1 with V1 with Q1, right? If you take inner product with V1 and Q1, then this guy is just going to be 1, right? So C1 over 1 over C1, this number is simply just Q1 transpose V1, okay? So what also, again, what if you take an inner product of this relation with Q2? Then this side is simply inner product of Q2 and V2. And Q2, V2, this is 1 and this is 0. So this is just 1 over C2, right? So you have this. So just go, you can go on like this all the way to the last equation. Then you can easily realize that these numbers, 1 over Ci is just inner product of the i's orthonormal basis vector and i's basis vector Vi. Okay. Okay. Okay, I'm good. All right. Okay. So now we are almost done. What I want to do is I want to translate this bunch of this K relation into a matrix relation. Just like this. Just first consider a matrix whose columns are the basis vectors from V1 to Vk. All right. And another matrix. This time, the columns of this matrix is from Q1 to Qk. They are actually they are not the same. They are two different matrices, but the dimensions of these two matrices are the same. They are both n by k matrix. Okay. Okay. Now things are getting tricky. Not tricky, but well, interesting. Just let me go back to the first relation. V1 is which is the first column of the left hand side. V1 is just simply C1 over C1 times Q1. And all the remaining plus there is plus invisible 0 times Q2, 0 times Q3, and 0 times Qk. So, and also we know 1 over C1 is just Q1 transpose V1. Okay. So maybe I may be able to say the first column of the matrix is this, and all the other guys below there, 0. Underneath, then this number times Q1 plus this number times Q2, this number times Q3, this number times QK, which is the first column, is going to be the first column on the left-hand side. So this precisely realizes the first equation. Okay. Okay. Let me go to the second column. Q1 transpose V. V2. Q2 transpose V2. And all the other number, all the rest numbers underneath equals to 0. In this case, this is the second column, and this means this number times this number times this number times is this, and this number times this is that, and all the other guys 0, and 0 this number times this this number times this equals to, since this is the second column, must be the same as the second column over here, which precisely realizes the second relation. Okay, can you see the pattern here? Okay, all right. Now I feel like I have to speed up a little bit. And Q1 T V3 and Q2 T V3 and Q3 T V3 and 0, 0, 0, should be V3 over here. Okay. So so Q1T VK, Q2T VK, QKT, not QK, sorry. Q3T VK, QKT VK. Okay, great. In our book, they say this matrix is A, this is Q, and this is R. What are the dimensions of these matrices? This is N by K matrix. This is again another N by K matrix. This is K by K matrix. So very interesting thing is happening here. So this is like this. Just try to think of any N by K matrix with independent columns. Well, if you have such a matrix A, then because of the Gram-Schmidt algorithm, you are always 100% sure that this matrix can be written as a product of matrix Q, which consists of also normal vectors, columns, times K by K upper triangular matrix. There always is such a factorization, as long as your matrix A has independent columns. Right? Okay. Yeah. Okay. So they say this is A equals QR factorization. Or just simply we say QR factorization. Okay. Just one more thing to prove. I have to also make sure that the span of these guys, the span of these basis vectors equals to the span of these orthonormal basis vectors. For each basis vector Vi, every basis vector can be written as a linear combinations of from Q1 to Qk. Okay, so this implies that every basis vector is a member of the span of Q1 to Qk. Therefore, and we know the basis, the original subspace V was a span of each of these basis vectors. So this guy is a subset of span of Q1 Qk. Okay, so one-sided inclusion is true. What about the other side of inclusion? No. Oh, so for the other side of inclusion, for the other inclusion, sorry. Oh, first you have to notice that all these are k by k, these are square matrix, and these diagonal entries are all non-zero numbers. Why? Because these diagonal numbers are actually turns out was actually 1 over ci's, and this number can never equals to 0, right? So therefore, this is an upper triangular matrix whose diagonal entries are all non-zero numbers, which is a full-length matrix. Therefore, this is always invertible. Okay. R has an inverse. So A equals QR implies Q is A times R inverse. Okay. Oh, well, A equals QR. That meant every column of this guy, every column of the matrix A can be written as a linear combinations of the basis vectors of Q, columns of Q. So by using the same logic, this equation implies every column of this matrix can be written as a linear combinations of columns of this matrix. So every Qi is a member of span of V12, Vk, which is V. So span of Q12, Qk is a subset of V. Okay. So we got the orthonormal basis. So okay, so let me summarize this. What is the Gram-Schmidt algorithm? So Gram-Schmidt algorithm gives you this. For any subspace and its basis, then it is going to give you an orthonormal basis, vectors of the basis of the space. Space, yeah, that's it. Yeah, I always feel like I need to summarize this whole thing by using one single theorem, which is about QR factorization. Every n by k matrix with independent columns. Yeah, this is very important. Can be written as QR, where Q is n by k matrix with also normal columns, and R is k by k matrix, which is invertible and upper triangular. So this is the theorem on the QR factorization. Okay, great. Okay, so we have spent too much time explaining the theory, and now this is time for some examples. Yeah, QR factorization, in theory, there is nothing too much complicated, so it's just a bunch of computation. But in practice, since it involves too many computations and normalization, so it requires a little bit of practice in order to get used to it. I have these three vectors. They are the three-dimensional vectors. Question is, are they linearly independent? Yeah, I have very strong feeling that they must be linearly independent. Why? Can I justify this? Yeah, sure. Yeah. So let me imagine a matrix whose first column is this, second column is that, and the last column is this. Then that is going to be a upper triangle, 3x3 upper triangular matrix with full pivot. So has must be invertible, right? So they are linearly independent. Great. So therefore, the span of this basis vector is going to be R3 itself. Now the question is, I want to find the also normal basis vectors applying the Gram-Schmidt algorithm towards these three vectors. And I want to get an also normal basis vectors. What is Q1? Q1 is a normalization of V1. So the length of this guy is just square root of 2. So 1, 0, and 1. Okay, not a big deal. What about Q2? Q2 is to normalize V2 minus Q1 T V1 Q1. This is yeah. So this is 1, 0, 0 minus this is Q1 and sorry, I messed up. I am sorry. It must be Q2. Okay. This guy inner product with this, which is just simply 1 over 2. 1 over 2. And V2 is just 1 0, 0. Sorry. What am I doing here? Yeah, I'm losing my concentration. So this is negative 1 over 2 and 0 and positive, negative. Good. Okay, I want to normalize this. This is parallel to 1, 0, minus 1, and 1, 0, minus 1 has length square root of 2. So this is this is 1 square root, so length is square root of 2, and divide by 1, 0, and minus 1. Which is 1 over square root of 2, 0, and minus 1 over square root of 2. Okay, great. Finally, Q3 is to normalize V3 minus Q1 inner product with V3, Q1 minus Q2 inner product of V3, Q2. Okay, so 2, 2, 1, 0, and V3 inner product with Q1 is 2, 1, 0. 2, which is just square root of 2, and this, sorry, it's getting tedious, and Q2 taking inner product with this with Q3, 2, again square root of 2, and 1 over square root of 2, 0, and minus 1 over square root of 2. This is oh, 0, 1, 0. Okay. Oh, all right. And its length is already 1, so there's nothing to normalize. So it's just simply 1, 0, 0, 1, and 0. Okay. All right. So this is Q3. Okay. So my matrix Q is consists of 3 columns, Q1, Q2, Q3. This is Q1. And this is Q2. And this is Q3. And A was what? A was this, and this. So 1, 0, 1, 1, 0, 0, and 2, 1, 0. And due to the QR factorization, this guy is Q times what is my R then? So, well, if you do not remember, just go back and look at this formula. So there are a bunch of inner product. Yeah. So I don't want to spend too much time on computing this. So just 1 over square root of 2, square root of 2, 1 over square root of 2, square root of 2, and 1. Okay. All right. Great. So this is the QR factorization. All right. So for rest of today's lecture, so I want to talk about the applications of the orthogonality. Okay, so far we mainly discussed on the vector space or the vector subspace of the Euclidean space. So our main playground was Rn, but there are much more than that. So well, in particular today I want to discuss more on the vector space of functions. And for vector space of functions, and in order to discuss the orthogonality of the vector space of functions, then first of all, we'll need to define what do I mean by two functions are orthogonal. Well, we know that we do know that the meaning of the two vectors are orthogonal, but what do I mean by what is the meaning of the two vectors or two functions are orthogonal? So this is very interesting question. And to discuss that, first we want to define the inner product in the vector space of functions. And I mean, to define that, and we actually have to characterize we have to actually need to pinpoint the characterizing property of the abstract inner product. So these are some key properties of the inner product. So I mean, in other words, these properties makes inner product indeed a inner product. Inner product. So, well, in general, an abstract inner product is this. Suppose I have any random abstract vector space. And I want to define a function which takes two vectors from V as an input, and it gives you back some real number. And we say this function is an inner product if and only if it satisfies these three properties. First, has to be commutative. And second, must be linear. A times V plus B times W. Z is A times B Z plus B times W and Z. And so, in other words, the linear product must be linear in the first slot, but because of property number one. So, well, linearity on the first slot automatically implies that there must be linear on the second slot too. And lastly, inner product of the two same vectors must be always greater than or equal to 0. And inner product of two same vectors equals to 0 if and only if V is the 0 vector. So for any abstract vector space B, if you can find a function satisfying all these three properties, then we define such a function as an inner product. So this is the definition of the abstract inner product. Let me just go back to, so these are our inner product in Euclidean space. And this inner product, well, clearly satisfying all these three conditions. So once we have this abstract inner product, now I am ready to give you the definition of the inner product in the space of vector space of functions. This is not just regular A, so this is a scripted H, or sometimes I say curly H. Curly H means space of all continuous functions defined on -pi to +pi. I mean, is it a vector space? Is H a vector space? Must be, because, well, if you just take any two random elements from H, they are two continuous functions on minus pi to plus pi. And if you add them together, then the resulting function must be also continuous from minus pi to plus pi. So this is closed under addition. And for any continuous functions on minus pi to plus pi, and if you multiply by any random number, then the resulting function is also going to be continuous function on minus pi to plus pi. So therefore, this space is closed under vector addition and the scalar multiplication. So this one must be a vector space, right? Now, what I want to do is I want to define a inner product in this space. How can I define inner product? Well, so if you want to multiply, so if you want to try a component-wise multiplication and addition, then you're going to fail because, well, because in this space, for any typical vector in this space, it doesn't have any component at all, right? So how do I define inner product? Just like this. Clearly, this is a function which takes two vectors from vector space H, and we'll give you some real number. So this is clearly a function from two vectors, vector space times vector space to real number. And is it commutative? Yeah, sure. F comma G, it must be the same as G comma F, obviously. And also, this is linear in the first slot because the integration is linear, right? So condition number 2 is also good, also true. And condition number 3 is also true because suppose that you plugged in two same functions, f comma f, and suppose that this guy equals to 0. Then f times f is f squared is the integrand of this integral. And also we know this guy is continuous. And for a non-negative continuous function as an integrand and the integral equals to 0, then there's only one option. The integrand must be 0, right? Therefore, the last condition is also true. Okay. So this is an inner product. This is actually an abstract inner product in vector space H. The surprising thing is this vector space has a basis. One cosine x sine x, cosine 2x sine 2x, cosine 3x sine 3x, and da da da. So these are all vectors in the vector space H, right? Because they are all continuous, right? And these infinitely many vectors, well, turns out to be an orthogonal basis. This is very interesting fact, which I can prove right now. And let me see if they are indeed orthogonal or not. Why? We take an inner product of sine mx times cosine nx, and by using the trigonometric identity. This is cosine m minus n times x minus cosine m plus n x and everything dx. So let us focus on this integrand here. This second integral automatically goes to 0, right? Because there's a, what is the period of this guy? 2 pi over n plus n. Therefore, if you integrate from minus pi to plus pi, then this guy is going to be 0, right? What about this one? Yeah, this one is also most likely goes to 0. Only one exception. What is that? If m equals to n, then this guy just vanishes, so this is just 1. And if you integrate 1 from minus pi to plus pi, this is going to be 2 pi, and combined by 1 over 2 over here, and the answer is going to be pi. Okay. So if m is different from n, 0, but if n is equals to n, it's going to be pi. Okay. Okay. All right. Yeah.
Cosine minus cosine is.
Oh. Sorry. I messed up, man. Sorry. My bad. Thanks for pointing this out. Yeah. Likewise, I can use the same technique, not the same technique, but almost the same technique to show that cosine mx times cosine nx integral. Also, I missed dx. It's again 0 if two indices different, but pi if two indices are the same. Lastly, cosine mx times sine nx dx. To integrate this, I am using another trig identity, but this time around, this is not just cosine something plus minus cosine of another thing, but this is sine of m minus x plus minus sine of m plus x. So in this case, so we have the two integrand regarding the sine functions. Therefore, in this case, no matter the indices of m and n, they are automatically equals to 0. So this guy equals to 0. Okay, so just taking a look of these three integrals, now I realize that these are indeed orthogonal bases, orthogonal vectors. Okay. All right, great. Now we know that these are orthogonal vectors. Also, it is known that this is an not just orthogonal vector, but they are orthogonal bases. That means every function in vector space H can be written as a linear combinations of these basis vectors. F is so 1, A0 times 1, and A1 times cosine x plus B1 times sine, A2 times cosine 2x plus B2 times sine 2x, and It goes along like this. So all I want to do here is I want to determine each of these coefficients. But to determine this coefficient is not a big deal, because you take the inner product of this function f. The inner product of this function f with cosine nx. If you take an inner product of f with cosine nx, then because of the orthogonality and linearity of the inner product, also all goes to 0, but a n cosine nx times cosine nx. So, and rest goes to 0. So an is just now we already know the answer. This is an times pi. Okay. Okay, and this is minus pi to pi fx cosine nx dx. Okay. And likewise, if you take the inner product with sine of n, this is just bn times sine nx. This guy only survives, and all the other guys, they got killed. And this is bn times b pi, and this is minus pi fx sine nx dx. And lastly, if you take the inner product with 1, this is then this a only this term survives. So a0 times 1 and 1. Well, this one requires a computation but 1 squared times dx, which is 2 pi times a0, and this is minus pi 2 pi fx dx. Okay, so an is 1 over pi fx cosine, and bn is 1 over pi sine, and a0 is, which is the only exception, 2 pi over minus pi fx dx. Okay, now we are almost done. So this relation can be written as 1 over 2 pi from minus pi to pi fx dx plus, this is an infinite sum, so let me use the sigma notation. An was this, so 1 over pi minus pi plus pi fx cosine nx dx times cosine nx and plus 1 over pi minus pi plus pi fx sine nx dx sine nx. This is called the Fourier series. I believe this is probably if I need to choose one most important identity in modern mathematics, then I'm going to choose the Fourier series. So this is a basis of the Fourier so-called the Fourier transformation. This is actually the Fourier transformation. So why is it so important? So this is so important in many different ways, but well, I will just focus on the signal processing. So why? So having so this identity implies that for every continuous function from minus pi plus pi can be written as a sum of constant function plus bunch of trig functions. Well, these are just some numbers. So therefore, this f can be written as some constant plus linear combinations of the sine and cosine functions. Okay. Now I want to consider like this. I will consider f as some signal in time domain, which lasts from minus pi to plus pi. And being able to decompose this guy as the trig functions implies that, that if you focus on this one trig function, then what is the frequency of this guy? The frequency of this guy is n, right? So therefore, which implies that the number, this coefficient that comes before the sine and cosine and x and the sine and x, these numbers, they represent the contribution of frequency and trig functions towards the original signal f. So if the absolute value of this number is large, then that means your original signal has quite large contribution from the frequency n signal. So you are actually decomposing a function you're decomposing a function in the time domain to the function in the frequency domain. Okay, so just looking at these numbers, then you can actually determine which frequency signal is contributing the most to your original signal. And being able to decompose, having such a nice decomposition enables us to have something like MP3s. So you know what MP3 is? So well, you have the you have the original signal, which is WAV file. But if you have the Fourier transformation of that signal, then you're going to have you can decompose your original music into a bunch of the frequencies. But our human ear cannot detect too high frequencies or too low frequencies. So why don't you just get rid of all those frequencies? And if you convert it to back, then you're going to get almost the same music, but the high frequencies and low frequencies has been discarded. So you saved lots of space. So this is how we get the MP series, but basically that is a bunch of the Fourier series. All right. My original plan was I was about to finish the chapter 3 on today's lecture, but well, unfortunately, so I don't have enough time. So maybe I'm gonna do a small tiny lecture on this Thursday, and we will see you on next Monday in the Gangdang. On Monday from 6 to 9. Okay. Okay. Thanks for your patience and see you then. See you on Thursday. Not see you then. Okay. Our exam will cover from the very beginning to the end of chapter 3.